Assalamualaikum to the both of the panel, Dr. Aida Fadhillah binti Abdul Qadir and Madam Anis Niza binti Rawani. My name is MUHAMAD Fadhillah bin IKHWANUDDin. I am the student of Dr. Junina binti Sardi. So I will present the official title for my project, which is the evaluation of energy storage benefit in distribution network with photovoltaic PV system. Actually, the title of my project has been changed due to the number of avoidable factor including the COVID-19 pandemic situation. Into the first slide, it is my personal details and the cover page for my PowerPoint presentation. Next is the content outline for the whole presentation. From there, we'll move into the introduction. So the introduction, energy storage widely used in a recent decade on power distribution for improved flow and technological efficiency. Energy storage is initially a battery that used mainly in the distribution system for the large-scale deployment because its implementation can solve several issues that had been arise on the system distribution side. This fundamental is developed because the energy has been generated cannot be destroyed or created, but it can be transferred from the one object to another object through the conversion. The technology provided from the application of energy storage is community energy storage that applied a distribution system near the residential area. The application of energy storage is based on where it is deployed, for example at the residential, commercial building, and etc. The problem statement slide is will closely follow into the introduction. The first thing is high electricity bill experienced by the customer because in Malaysia the rate of electricity tariff is the whether it is at peak hour or off peak hour, so the consumer will pay the same amount whether the user use the electricity or not. Secondly, the high amount of energy produced by the PV system, especially during the peak solar generation at noon. Third, the growing number of small-scale PV deployment has had multiple impact of power distribution systems such as a voltage drop and reverse power flow. And lastly, the cost to build the energy storage is quite high, so it can provide sufficient demand for user, especially in residential area. From there, the objective slide will be followed through. Firstly is to develop the IEEE 9-bus radial distribution network PV units and energy storage by using GridLab-D software. Then to evaluate the effectiveness of CAS deployment with the PV in terms of peak demand, voltage profile, and power losses in the distribution network. And lastly is to investigate the effect of PV distribution, energy storage size, and distribution on the technical performance of the distribution network. From there, we will move into the scope for this project. This project is more focused on strategically accommodate and operate CIS unit in distribution network, especially in residential, taking into consideration different technologies. Secondly is IEEE 9-bus radial distribution is used as the test system. The PV system with the size of 17442 meter square is added for the centralized location and 2180.5 meter square for the balanced distribution network. The coding parameters of the bus are using Notepad++ in GLM format before being run using the GridLab-D software. And also for this project, the lithium-ion battery were used in this project to analyze the performance of the energy storage system. From there, we will move into the literature review.
In this literature review, I will tell the energy storage as a whole. The first one is the benefit of energy storage. There are 4 benefits of energy storage that I got from the article and paper in the internet. The first one is environmental. Environmental benefit is based on factors such as location, power cost, and electricity load. The strategic energy storage may offer considerable cost advantage in those cases. Discharging energy by energy storage may reduce load during the peak time. It is resulting in decreased demand cost. Energy storage system accelerate the wider implementation of green energy by improving the overall efficiency of the power grid. Also, the energy storage provide an emission-free option that could be available for tax credit when paired with another environmentally sustainable technology. Energy storage also planning for emergency backup key is a key part of the resilient plan. It is because it can be minimize demand for charging, its reliability and availability in the case of power losses can be increased compared to a standalone battery used during a power voltage. Another benefit of energy storage is demand charge reduction. These charges are based on the 15-minute duration in which energy consumption is higher during the day and may in certain situations. Energy storage devices, in particular those combined with the intelligent software, will monitor the load of the facility and minimize demand charges by supplying battery power at the demand hour, essentially flattening the load. This demand charges reduction not always coincide with the peak usage building. Lastly is load shifting. It is a strategic technique that can reduce power consumption. In this case, special system will evaluate the consumption pattern and storage efficiency used to their full cost-saving capacity. Next, we go into type of energy storage. The first one is flywheel system. Flywheel may be applied hybridized with other ESS technologies, such as batteries to increase efficiency. Flywheel system also accelerate rotation to store energy and discharge by slowing down. A mechanical ESS that store energy from the grid and transform it to the rotating disk is a flywheel. Below, I attach the component of flywheel device. So, the next is BESS. Battery ESS are known as electrochemical devices providing electrical energy by chemical reaction conversion. Due to growing energy capacity and simple means of installation, recent development in batteries are attracted investors to build BESS. Lead-acid and lithium-based batteries are BESS, which are widely used for modern power grid applications. The electricity is converted while charging into chemical process by reverse electrochemical process. Then the next one is fuel cell. The properties of the fuel cell are similar to those of the battery but different in their mode of activity in the way that the fuel cell utilizes electricity generating fuel. Specifically, power production primarily absorbs hydrogen and other hydrocarbons because of its cleanliness, cost effectiveness and high efficiency, gaining interest among the researchers. Next is superconductor. Superconductor is the system of the power generation to fulfill the constantly changing power requirement. The gap in the ratio between the peak power and average power is high in the small household system. The larger the superconductor applied to the devices, the higher the effect on the battery lifetime.
So from there we'll move into the methodology for the whole project that we show the flowchart. So basically this is the whole flowchart for my FYP2 project. So after start we are moved into the literature review, and then we are identifying the network parameter, and then we create test model before we simulate the model system by using GridLabD software. And after that we are validating the model test. If the test model is not okay, we are go back into the simulate the model system using GridLabD software. If the system is okay, we are move into the result. And so this is the IEEE 9 bus radio distribution network that I use in this project. When generating the low voltage, basically we are using radial system because it uses less cable and ideal for the minimal load requirements. However, when the load far from the slack bus, the serious voltage fluctuation will happen. Next is the load profile and load parameter that I use for my project. Also the line parameter. These three parameters were taken on the research paper on the internet. So the nominal voltage that I use basically 23 kilovolt. So 23 kilovolt is for 3 phase, so I convert to per phase, so the value is 13279.06 volt per phase. Next is the energy storage, inverter and PV parameters that are used in GridLabD software. I'm using method load following and operation work in time changing loads. For the inverter, it will change the battery when the power is below the charge on threshold and stop charging when the power above charge off threshold. Meanwhile, the battery will stop charging if the battery below the discharge off threshold. Then for the PV solar unit model based on Solar Advisor model, which is SAM in GridLabD. Also, flat plate solar are used because it's more efficient and precise on the PV output power. So yeah, this is from GridLabD software. So far for my project, the system record for 24 hours with power flow module setting, and the climate module I use is from Seattle from United States. And the right picture shown that the load configuration and node for the slack bus, which is on the meter 0. For the load configuration on another meter beside meter 0, so the coding are shown just like a picture. So the left picture is the load configuration for the meter 1, and the right side is for the meter 8. Next is PV balance distribution. Basically for the PV, there are two cases, which is the PV balance distribution and PV centralized located. So this is for the PV balance distribution, which is each bus will insert a PV to be tested, and the area of the PV also will divide it into 9, because in my project I have 9 bus to be edited. Next one is a PV on centralized located distribution network. So this PV is located only at one bus, which is bus 4 with the area of 174,420 meters squared. Next is for energy storage. This is the coding for energy storage. The result basically is based on charge and discharge on threshold. The energy storage will charge the battery if the downstream power is below the charge on threshold and stop charging when the power above the charge of threshold. Moreover, the battery will stop discharge if the power below the discharge of threshold, and the battery will discharge when the downstream power is above the discharge on threshold. So lastly, after done with the coding, I will run the Notepad++, and the output data will be generated based on the coding. So basically this is the file for output data that I've been create on the GridLabD. So the file player that I need to create is 10 file, and the output file from GridLabD with the format comma separator value CSV, which is also in Excel. We'll finally move into the result that will be identical to the final result for this project. So the result of the simulation are from 9 bus radial distribution. For the result, there are a few cases that have been identified in this project, which is the comparison the system before and after at the energy storage, with the sub case is the effect of energy storage size, and also number 2 is the evaluation the effect of PV and energy storage for the balance distribution and centralized located distribution. So basically, before we are at energy storage to the system, the power at the slack bus must be identified, and hourly demand power at the slack bus before at the energy storage is displayed below, which is the blue color. Then after that, in GridLabD, the charge on threshold is set into 5000 kilowatt, and the battery will act by the load, and the discharge on threshold are set on 10200 kilowatt power by the battery act like a generator for minimize the peak demand. After adding storage to the system, SOC also can be analyzed. For the SOC, it is important that when the energy storage is discharging, it must be or near to 0.4 to make sure that the system can be used for the next day. Second one is the power losses. It's shown that after adding the energy storage, so the power system at the peak hour are lower than before adding the energy storage. For the sub-cases, which is the effect of energy storage size. So when we are increasing the size of energy storage, it clearly shows that the power losses with the biggest size will reduce by 10.88%. Next one, the right picture shown that for the demand profile, that shown that the AES with the biggest size will charge higher and discharge lower than the energy storage with the 12 megawatt hour. Second one is the state of charge between two different size. So the battery will start to charging 5 hour and the SOC increase until it's fully charged, which is near to 0.6. Both 12 megawatt hour and 24 megawatt hour takes 5 hour until it's charged. For 12 megawatt hour, it decreases rapidly, discharge and back to near 0.4 of SOC. For 24 megawatt hour, it decreases a little bit slow. So basically, from the state of charge, make sure that when charging, the value of SOC need to be equal or higher than 0.4, because from the coding we are set the state of charge is 0.4, so we must follow from the coding. So the right picture is shown that the voltage profile between the two sizes, which is the voltage profile for energy storage with 24 megawatt hour is higher than the energy storage with a 12 megawatt hour. So it's shown that energy storage with the biggest size is good than the 12 megawatt hour. For the next is the evaluation effect of PV photovoltaic distribution. So the balance distribution is PV is added at every single bus except the slack bus. Meanwhile, the centralized located distribution is PV is added at the one bus only, which is the bus 4. For example, in my project, one PV system with the size of 174420 meter squared for centralized located, and 9 PV system with the size of 21802.5 meter squared for each for balance distributed. So this is the coding, and this is the demand profile at the slack bus between the balance distribution and the centralized located distribution. And also from this comparison, it can be seen that the present of balance distribution, the power losses at the slack bus is less compared to the centralized located. It clearly shown that when we are using the balance distribution, it make the power losses more lower than the centralized located. And next is voltage profile at the critical bus. Critical bus is weakest bus as it can withstand small amount of load before it causing the voltage collapse. So I choose bus 9 because the bus 9 is far from the slack bus. So it's shown that a balanced distribution has a higher voltage profile than a centralized located. So it's shown that a balanced distribution is the good method that we can use for the photovoltaic distribution. Last but not least, we are the closest we are ever been at the end of this presentation, as the slide that will conclude for this whole presentation. So the integration of energy storage in distribution system with the PV have achieved the several technical benefit as follows. The peak demand has reduced by 8.33% when the ES with a size of 24 megawatt hour is deployed in the system. Also, the energy losses has reduced by 10.88%, and voltage profile has improved where occurrence of voltage violation had reduced by 0.814. Next is evaluation on the PV distribution, shown that the balanced PV distributions outperform centralized PV distribution. The balanced PV distribution recorded a 6.6 lower power losses, 0.89% lower peak demand, and better voltage profile than the centralized PV distribution. This result demonstrates that it is better to have a several small size PV system distributed in distribution network compared to the large PV system in centralized location. It also can be concluded that the objective have been achieved. For the future work and result, this system can be used more system buses and use different energy storage dispatch strategy to ensure the effectiveness of the use of energy storage in the residential distribution. And lastly, a more higher load data and higher percentage of PV penetration is recommended for the future work.